Welcome to the almost sediment episode of The Rug. None of this is mobile bed, the kind of stuff that Alex and I do, but it's all kind of sediment adjacent, which is how people generally like their sediment, is maybe adjacent rather than the main deal. So I'm going to talk about bridge scour. And I would also like to recognize Anton Roeder-Siren, because all the bridge scour tools I'm going to show you, he wrote. As the sediment specialist, I get to envision these things, but when it comes to who actually developed these, you can thank Anton for that. 2 parts. I'll talk about bridge scour, and then I'm really looking forward, actually myself, to Alex's content on secondary currents. It is kind of game changing. All right. I asked the robot to put together a summary of the original DOS programs. It did a pretty good job. I actually even like the Atari DOS font it used. When I came into the Corps, I knew about HEC-2. And I quickly learned about HEC-1, and then I became the Buffalo District sediment guy, so I learned about HEC-6. Somewhere along the line, I heard there was a 5. 3 and 4 are kind of lesser known, but I assumed that they existed, and I just kind of assumed that everything led to sediment, that the world culminated in HEC-6. And so I was at lunch one day at the Buffalo District, and someone mentioned HEC-18, and I thought, oh, there are 12 HEC programs that I am unaware of. That turns out not to be the case. HEC-18 doesn't stand for Hydrologic Engineering Center. It stands for Hydraulic Engineering Circular 18 from Federal Highway. This is the bridge scour analysis guidance that all federal and most state agencies use to evaluate bridge scour. You probably know, but just in case you don't, bridges fail because of scour. HEC-18 argues that, scour of footings and abutments during floods is the #1 reason for bridge failure. The USGS did a similar study. They said about 60% of bridges fail because of scour. There have been independent reviews. Between 1993 and 1995, about 3,600 bridges in the U.S. alone were damaged or destroyed because of bridge scour in 4 separate events in 4 separate regions. Bridge scour is kind of a big deal. It's been one of the primary uses for RAS in the private sector. Just to give you the context, bridge scour isn't a thing. It's a series of cumulative effects. There are 4 different reasons why you might undermine a bridge with a mobile bed boundary. And so here I've got a bridge, schematic with our abutment and our footing and our pier and some piles underneath it. And then this is the design bed elevation, which is very safe. But there are 4 things that can happen to make that unsafe. The first is just regional erosion. The bed elevation can lower because of regional processes. Head cuts can come up through. That's the realm of mobile bed or geomorphic analysis. That is not scour. That's a regional process, but you still have to consider it. The next 3 are more local processes. The next one's contraction scour. So, you've got flow going from a wide conveyance area to a narrow conveyance area. It's going to speed up. That contraction causes scour. And then we have what are called the local effects. The effects, which are 3D effects of the water hitting the actual structures that are holding the dam up. And so we have what's called pier scour that happens right at the pier, and abutment scour. And so these 4 things conspire to undermine our bridges. And the last 3 are what we call scour. We distinguish between erosion or incision, which is a regional process, and scour, which is something that happens locally because of local effects. And HEC-18 is the tool that we use to compute scour. Now, the actual tool that people used to use to do this was the HEC-18 bridge scour tool in RAS. This actually predates me. Mark and Chris Cadell wrote this before I joined the Corps, so we're talking a couple of decades ago, but it used to be the tool. If you worked in the private sector and used RAS, you were probably doing flood insurance studies or bridge scour. It's remarkable to think about the number of 4 cross-section models there used to be just to compute bridge scour. But over the years, this fell out of practice, and eventually Federal Highway started recommending against it for 2 reasons. One, HEC-18 updated. We are compliant with the 2001 version, and they have a 2012 version. They have another one in draft too, so there'll be future updates. Then secondly, there's a kind of a shop within Federal Highway that started to argue that we should be really using 2D hydraulics for bridge scour analysis. This is something I feel a little bit ambivalent about, since these bridge scour equations are kind of lumped parameter, but there are some places where 2D hydraulics do give you an advantage. And so Federal Highway wrote their own hydraulic toolbox that you could kind of either manually input the data, or you could extract it from other two-dimensional models. And we went back from the world where everyone was using RAS to where a lot of people had their own spreadsheets, including in the core. So two things happened in the last 5 years that made us kind of rethink about how we're going to do bridge scour in RAS. The first one is 2D bridge modeling has gotten a lot better in RAS. Kind of every release in the 6X series, bridge modeling got better, culminating with this really excellent 2D bridge, pressure overtopping model that we can do. And then second, the Philly district, they are the CX for bridge scour in the Corps of Engineers. And Federal Highway told them, well, you really need to use 2D. And we started having this conversation of, yeah, but can we use RAS? And so Philly district found some money, and we decided to make RAS compliant with bridge scour and then add tools to make it easy. So 4 steps. The first step is I had to understand what we were doing in bridges. Because bridges changed from 6.1 to 6.2 to 6.3 to 6.4, and I ended up teaching that several times, I realized almost every one of those releases, we changed the way bridges work in RAS. Every one of those releases, we made it better, but it turned out I didn't actually even understand what was happening in bridges. And if I don't understand, then you are definitely forgiven for not understanding how bridges work in RAS. So we kind of put together some modeling tutorials and explainers. Since 7.0 is the end until we do it better in RAS 2025, we put together some best practices, even for things that are very bridge scour oriented, like, what are the best practices for aligning piers, and we made some videos and tools to help you kind of build your bridge scour model. The second thing we had to do was we had to write the right data to the reference lines. Because the bridge scour equations are essentially one-dimensional equations, using a 2D model, you have to go to some sort of one-dimensionalized realization of that. And so when we started writing reference lines, it became possible for us to start kind of doing cross-sectional averages or cross-sectional maxes, which is what we need. The next step was to populate these reference lines with the bridge scour data. And so you need 3 sets of reference lines in order to do bridge scour. This is actually the main work of doing a bridge scour model, because all of the math is done for you. This is the art. The art of bridge scour, and I've been working a lot with Federal Highway and people who used to work with Federal Highway, interacting with them about how you actually build a bridge scour model. And a lot of it comes down to getting these cross sections right. You're going to digitize 3 sets of cross sections, except each of those cross sections has 3 reference lines, 1 for the channel and 2 for the overbanks. So the first one that you're going to define is essentially the bridge cross-section, except we call this the contraction cross-section. I'm trying to be very careful to use the Federal Highway language. I find the notation in HEC 18 very confusing, and the language is actually also a little confusing. And so I'm trying to use their language precisely so that as we move between tools, you will get less confused. So the contraction cross-section has 3 parts, 3 reference lines, a channel, and the overbanks. Now, the first thing you need to know is that the channel in bridge scour is different than the channel in 1D hydraulics, right? For those of you who build 1D models, you think the channel goes from like the channel bank to the channel bank. That's for blue water people. If you're coming to the bridge scour world, you need to start thinking morphologically, because scour is a morphological process. And for a morphological process, the channel is actually the transportable bed. And so it actually goes from the toe of the bank to the toe of the bank. And then the overbank starts at the toe and goes up into the floodplain. Okay, so then the second cross-section you need is what we call the approach cross-section. The approach cross-section should be upstream where the flow is fully developed at its maximum width, because some of the equations look at, how do things change from the maximum width to the minimum width. And so same thing, 3 reference lines to define, and these reference lines should essentially just abut. They should be, neighborly. They should be connected, but not overlapping, to define your approach cross-section. And then this is different if you used to do 1D, because for 1D, we used the same cross-section for both of these, but you need a third cross-section, which we call the Pier approach cross-section. Again, this is where the language gets a little bit confusing because you have two approach cross-sections. You have an approach cross-section and then a Pier approach cross-section. We only use this for Pier Scour, and it is 1 pier length upstream. And so you have these 3 cross-sections or 9 reference lines. Here's something a little more realistic. Here's an actual river with these laid out. The reason I show you this is because one of the things you can see that up here, we have our contraction cross-section and then our pier approach cross-section is really close to it, 1 pier length. But then our approach cross-section is pretty substantially upstream. And in interacting with Federal Highway, one of the things that they've said to me is that people put their approach cross-sections too close to the bridge. You need to actually look at where is flow fully expanded, because this is all part of the contraction process that will lead to scour. All right, so the third step was, now that we're writing everything that we need for a bridge scour approach to the reference line, now we have to make it available. And so if you right-click on the result, you'll get this show results table. And you'll notice there are things in here that lots of people would be interested in. Like, I don't know, anyone interested in an average flow or an average velocity? These are things that we've wanted for a long time, right? But then there's some like weirder stuff. Part of that is that we populated this table with everything you would need for bridge scour. And this is the first time that like compliant bridge scour was actually possible in HEC-RAS. And so you'll see the documentation has like remnants of the way that we used to do this. Is then I just kind of built some explainers on how to copy and paste the data you needed into the Federal Highway Scour tool to get the scour analysis. And so at this point, it was technically possible, but it wasn't fun. So Anton made it fun. We added a bridge scour tool that automatically writes the data that you need to the Federal Highway Toolbox file format. And so you can just open it up in the toolbox. And so instead of showing you slides, I'm just going to demo that. We have a couple example data sets here. This is one of them. And I'll just kind of show you how to draw the reference lines here. This is a pretty interesting bridge. There's a lot going on here. And so the first thing we're going to do is we're going to come in here and we're going to draw our reference lines. If I go down here and select reference line, the first reference line I need is the contraction reference line in the channel. Remember, each cross section has 3 reference lines. And so the channel is going to go from toe to toe. And it's important to give these names that will tell you the story later. So we'll call this contraction channel. Public spelling is always a little bit of a challenge. And then you will put one over here and call this contraction right over bank, and so on. And you'll do that for all 9 of these cross sections. The pier approach cross section here is easy because it's just going to be upstream. But where does the approach cross section go? You actually want to run the model and look at your flow paths to determine where the approach cross section is going to be, because it's got to be at maximum width. And it turns out for this model, the maximum width is really pretty close to the bridge. And actually, Federal Highway asked me not to use this model as my example model because they thought that having the approach cross-section this close would help build bad habits, where we should generally be looking farther upstream. But this is where the art comes in. You're not mechanically drawing these cross-sections. It's back to the old days of thinking about what a cross-section looks like and what it's for. Okay, so let's go to our idealized model now. This is the model that I am releasing with the software. You can see I have my reference lines set up. I have my contraction cross-section here, then my pier approach here, and then I've looked at my flow fields and have got my approach cross-sections upstream where the flow field is fully expanded. Okay, so what we're going to do now that I have a result is I'm just going to right-click on the result, and I can come here and say show results table, and that will give me all the data that I need. But now Anton's added this tool, show bridge scour tool. Yes, this is beta. We had a bug in 7.0. So if you're doing this, make sure you're in 7.01. And because bridge scour is a life safety risk, I want to make sure that we're doing this right. I want to get some testing before we take this beta tag off. So please test this and please get your feedback back to us. We're hoping for, late this calendar year to take that beta tag off. And so if I do that, well, I get the bridge scour tool. Now, the first thing that you get in the bridge scour tool is you get a schematic of the bridge itself. And these are all the things that are defined in the deck. Now, this is the first confusing thing, because if you look at the way I built this bridge, I have both the abutments or the embankments and the piers burned into the terrain. But then I also have them defined in the deck. And this is one of the things that confuses and sometimes bothers people, is our current guidance is that your abutments and your piers should be in both places. And people get very concerned about that because they think we're going to double count. We have a whole video on that. Let me just tell you, we're not. We are not double counting if you put them in both places. And by defining them in your bridge deck, that's how we know what they are, so we can send them to the Federal Highway tools. So unless you define them in your bridge deck, we won't know that you have abutments or piers when we send it to the tool. And so this is just to show you the geometry of the bridge we're going to send to the Federal Highway toolbox to make sure that it's what you think it is. There's actually no editing here. And then you'll see that there are 3 different tabs for the 3 different types of analysis. So let's start with contraction analysis. For the contraction analysis, you need 6 reference lines. So, essentially what the contraction analysis does is it compares, the flow at the approach cross-section to the flow at the contraction cross-section. So you're going to ignore this pure approach cross-section, and it says, what's your contraction leftover bank? Well, Anton made this cool tool where we can actually just go pick it, and it will populate the hydraulics needed for this analysis. And so what's your contraction channel? We can go pick it. But the other thing you can do is you can just choose the drop down. And this is really nice because I've given them good names. And so I'm going to go get the approach leftover bank, the approach channel, and the approach right over bank. And what you'll notice is that throughout this tool, the only thing you're doing is choosing reference lines. That's the work of this part of the modeling, is you're going to lay out your reference lines in good places, and then you're going to choose them. Okay, for peer evaluation, this gets a little bit more complicated. It seems like it would be easy, but you actually have to think about this morphologically. This is the thing I've learned most about bridge scour analysis over the course of the last year, is that it's not mechanical. You have to think about, what is the morphological future? What's going to happen? So these are pretty obvious. These piers, we're going to use the pier approach cross-section for the channel. And I would say this one is also pretty obvious. For this one on the left, we're going to use the pier approach for the leftover bank. But these are less obvious. And for that, let's go back to our kind of more complicated result. So in this case, these are obvious. For these, we want to use the channel hydraulics. These are also pretty obvious. For these, we want to use the overbank hydraulics. But what about these? Are these channel or are these overbank? Well, strictly, our channel hydraulics, remember, for pier scour is toe to toe. So these are officially overbank or floodplain piers. But the question you want to ask is, will they remain that way? In soccer coaching, one of the things we tell the kids is that you don't want to play the ball to the player. You want to play the ball to the future. You want to play the ball to where the player is going. And the thing I've learned about bridge scour analysis is you want to do the scour analysis, not for where the river is now, but for where the river could be. And so this is practically in the channel. So we're going to use channel hydraulics for that. And this river bends this way, which means that it could migrate into this pier. And so we're going to use channel hydraulics for that as well. Going back to our demo, let's just say, somewhat arbitrarily, just for the sake of the demo, that we've gone out to the site, of course, and brought a geomorphologist with us and said, what is the risk of this channel migrating? And we'll say, I don't think it's going to migrate into that one, but it could migrate in this direction. And then this pier becomes a channel pier, essentially. And so we're going to use pier approach channel for that one and pier approach leftover bank for that one. Okay, but we're not done. Piers are most complicated. We have this other decision we have to make, is what's the reference point? Is the reference point Thalweg or local? Well, let's go back to our morphological thinking. Local is what you would expect. Basically, we compute a pier scour depth, and then we just add it to whatever the elevation is there. And that's fine, unless you expect the channel to move. And so a lot of this is built around kind of Western or Alaska rivers where they're braided, and the Thalweg could be anywhere at the end of the flood. And so if you think that the river might move into the pier, well, then you actually want to add your scour depth to the worst possible condition, which is the Thalweg. The ones we chose the overbank for, we make local, but the other ones we leave Thalweg. Okay, one more. The abutment. There are two approaches to abutment. You can have the channel or you can have the overbanks. Same idea. Like, do we think the channel could erode into the abutment and make it actually a channel setting? And so in this case, let's say we don't think that about the left one, but we do think it about the right one. So the left one will be condition B, overbanks, and the right one will use the channel hydraulics for, because we think the channel could migrate into it. And what Anton has done here is he said, okay, this gets confusing, so let me tell you which cross-section you need. Here you want the contraction leftover bank, so let's go contraction leftover bank. And for the approach, you also want the leftover bank, so that's pretty straightforward. For the channel condition, you still want the contraction to be the right overbank, but you want the approach to be the channel. And we could go into more detail about why that is, but that's what's required, and it goes and gets the appropriate hydraulics for each. Okay, so all you've done in the tool is chosen cross sections. Now we have a summary of the export, and if you go to export all, we can call this rug scour demo. And it is creating an HYD file. That HYD file is the file required by the hydraulic toolbox. And so if I open the Federal Highway Hydraulic Toolbox, which is on, I can just go in and directly import that file, rug scour demo. You can see my practices there. And then hopefully you get this error message because 5.5 changed the way they store the grain size. It's okay. We'll live. And so now if you just double click on the bridge scour analysis, you can see that this is the tool. We'll put out some videos dealing with this in more detail and talking about how it interacts with the equations. There's really only a few things that you have to put in here. Now, of course, you should be looking at everything and evaluating every decision and evaluating the results. We'll do more videos on that. But just to show you, you actually only need to put 3 numbers in here. First, it won't let you do anything until you define the bed gradation. That's the change they made in 5.5. It is, but we're going to go to define gradations, and then we're going to push a bunch of buttons. Add gradation, define gradation, define gradation. And all we need is a D50. So they have this 50th percentile. And so I'm just going to make my D50 0.2. And OK through all of those. You see they're green, which means I'm compliant now. And then the other thing I need are my bank stations. Well, here we have this really helpful tool back in HEC-RAS. If you're at Cameron's webinar the other day, you saw that we actually have now a lot of really cool visualizations for our structures. If I look at my structure plot, I can come in here and I can see, remember, my channel banks are actually my toes. So it's 137 and 187. Okay, so I'll come back to the scour tool and I'll say my banks are 137 and 187. And now if I come in and I define my scour parameters, if I just choose that bed gradation, it will go through and compute my clear water scour, my live bed scour, and my overall scour, contraction scour is about 2 feet. Okay, my piers, you need no additional information. So you can just go in and define your piers. You have to make some choices about what the pier geometry is and clear water, or are there dunes. But here you'll see that we are getting pier scour on the order of about 5 feet. And then you also have to define the gradation for your abutment scour. At the bottom here, we go to abutment and define the parameters and define the bed gradation. Now we have everything we need, and we can push plot preview, and we get a scour result where this green line is the contraction scour. That's how much scour we get from going from a wide floodplain to a narrow floodplain. The reds are the pier scour, which these were local. This one was Thalweg, remember? So the scour is added to the Thalweg of the channel. We have our abutment scours here. And that gives you the guidelines of how deep you need to make the footings, or the risk associated with the bridge.